All right. Okay. Good morning, everyone. Welcome to today's talk. And we are very happy to have Professor Hatice from University of Cambridge coming to visit us and give an invited talk today. And Professor Hatice is a full professor of affective intelligence and robotics at University of Cambridge, where she directs the AFAR lab and serves as associate director of the Center for Human-Inspired Artificial Intelligence. Her research advances multimodal and social intelligence for AI systems, particularly embodied agents and robots, by integrating machine learning, affective computing, social human non-verbal behavior with a strong emphasis on well-being, fairness, and explainability. That is the focus of today's talk. She has published over 190 papers and has been consistently recognized among the Stanford University Award of Synthetics. Professor Bunnes has received a number of international awards, such as being named as the honoree for the Sony Women in Technology Award with Nature 2025 for her contributions to effective computing and human-robot interaction, and has held leading roles in major conferences and journals, including serving as the president of the Association for the Advancement of Effective Computing. Her research is supported by major funding bodies and industry partners, including ESRC, EU, and Enduring Institute, and Google. Before we begin the talk, I would like to mention that Hatice's talk also forms part of our new ELLIS Institute Finland's distinguished lecture series. So I'd like to now invite Jiancheng to briefly introduce the initiative. Jiancheng, please.
Yeah, hello. Good morning, everyone. I'm Jiancheng Yang from ELLIS Institute of Finland and
Just a moment. Let me see. We cannot see your slides.
It's because it's extended. Let me change the.
Yeah.
Yes, I'm actually sharing.
That's
I'm just duplicating the slides. Yeah, I think. Yeah. Oh no.
We have it there on the corner, and so get it today. Yes, now it's here. Just continue, Jiancheng.
Okay, yes, good morning. Yeah, I'm Jiancheng from ELLIS Institute of Finland and Aalto University. And on behalf of ELLIS Institute of Finland, I would like to warmly welcome you to the ELLIS Distinguished Lecture Series. This series continue a strong tradition of distinguished lecture previously established within FCI and now carrying forward under the ELLIS Institute. And the European Laboratory of Learning and Intelligence System, or ELLIS, is a pan-European network dedicated to strengthening Europe's leadership in AI through scientific excellence and cross-border collaboration. And today, the network brings together more than 1,800 members across 44 sites in 17 countries. Through its program and joint supervision model, it connects researchers across Europe and support the next generation of AI scientists. At ELLIS in Finland, we build on this network with three pillars: research excellence, large-scale collaboration, and strong global partnership. Our research strategy centers on fundamentals of applied AI. We build on fundamental AI research while advancing strategic application domain. Health is our first strategic application area, but our ambitions span more broadly. With a distinguished lecture series, our goal is very simple. We would like to bring leader researcher to our community, foster dialogue across field, and shape a scientific direction of AI. And we are very happy to continue this tradition and look forward to many inspiring lectures ahead. And thanks for joining us today. And let's welcome Professor Hatice Ganas. Thank you.
Thank you very much, Jiancheng. And without further delay, and let's welcome Professor Goodness to the stage.
Thank you. I just have to go back to my display settings. It's, trick. Yeah, everyone can see? Yes.
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 Perfect.
Okay.
Thank you very much, everyone, for inviting me, first of all, Professor Going, and also being here today. So I'll be talking about fairness and its applications also to health-related aspects. It was great to hear that in terms of ELLIS Finland, this is one of the main application areas. So I'll try to link to that. So that's perfect. So AI bias internationally has been an issue for quite some time now, since in fact when artificial intelligence started making its way to real-world applications, it became more prominent because it was when it's only in the lab, right? Nobody cares as much because it doesn't have implications. But as soon as we start taking things out in terms of face recognition systems at the airports, or robots, or even healthcare applications, or when we decide to whom we're going to give certain jobs, when we are interviewing people, and if we're using AI to do these things, it becomes really important. And here I just put some in the generic media, some of the concerns, but obviously it has grown, even multiplied with the use of foundation and large language models. So initially it started with one of the pioneering works was by Jebru's team back in 2018. And this is what probably brought it to the media attention. So what they were trying to do is to evaluate some of the major gender classification systems, including by companies like IBM and Microsoft. And what they reported is, particularly for gender classification, as the skin tone starts becoming darker, I'm testing it, but I can't see it. So it doesn't work. But as it starts becoming darker, actually, as you see, classification rate becomes almost close to chance level. So this is one of the first works to sort of highlight this. Of course, once this was reported, the major companies started working on this area. But also, even using AI for job applications, I mean, forget about the skin tone. If you just change a little bit the brightness, actually, the prediction outcome is changing. So all of this starts bringing to attention, okay, particularly for computer vision, this is what I'm giving examples, but doesn't apply only to computer vision. You know, what are the issues and what should be done about this? So fairness is part of AI ethics these days, and different institutions and different governments have listed these actionable guidelines or principles. These are from the UK government, from their website. So there are things like privacy, transparency, explainability, and many more. And fairness at the moment is a bit bolder because that's my focus. But what it's saying there is you should design your AI system not to discriminate against individuals, communities, or groups. So this is one of the guidelines on the UK website in terms of what AI fairness for generic lay terms would mean. So because I'll be linking to socio-affective systems, I just would like to bring us on the same page in case there are people from different backgrounds, what we mean by sort of closed loop socio-affective systems and interactions. So we have the user and we sort of need to sense the user via different sensors. This could be vision-based, audio, even biosignal, or other modalities, it could be even touch sensors. Then, of course, we have data, or we might need to acquire the data depending on the application. But because it also links to other domains, for instance, when we talk about health and well-being, as computer scientists, we are not experts in those areas, right? So you really need to have this interdisciplinary understanding, and I call it background research, but what are the models, what are the definitions of the phenomena. We need to have an understanding from these different areas. So it feeds into our models in that sort of foundational level, even in terms of what labels and what sort of data we need to gather. So once we have data and some labels, and depending on the domain, this might need to be expert labels, then of course we need to do some sort of feature extraction and train models to recognize, predict. And then, for instance, let's say at a very sort of simple level, if our system detected that the person is smiling, does our work finish there? Well, no, because we need to understand, is the person smiling because they're happy? Or is the person smiling because they're embarrassed? Because there's work showing that people smile when they're embarrassed as well. So that means we need to have this context-sensitive interpretation. So we need to have a way of modeling context. And that's a very big and open research question even today. And what does it mean? So it means to try to answer the big 5 W questions as much as possible. And these are, who is our user? What are they doing? So what is their task? Where are they? So what is the environment? With whom are they? Meaning, are they alone or with some other social context is involved in there? And then, if you can also answer, why are they? So, how do they feel? So these are all big W5 plus questions. This should help us interpret what we sensed and predicted in a context-sensitive manner. And then, once we have this on the system side, and the system can be, for instance, virtual reality gaming for cognitive training, or your mobile system, or hybrid system, or robotic system. So on the system side, we also need to do context-sensitive responding, right? And that would mean seeing these in the behavior of the system. So somehow the system should have this imbued understanding. And the interaction keeps going. So that's what we mean by closed loop interaction. So just sensing is not enough, right? Because we need to see what happens to the humans when this sort of sensing is occurring. So this is what I'll be basing my talk on in terms of detection. And this part I call a generation, because it's the system needs to generate some behaviors. So within these sort of definitions, what I'll talk about is I'll explore a little bit definitions and types of bias. And then I will focus on bias in the sensing aspect, looking at how we can evaluate, how we can do fairness analysis, how we can mitigate and achieve fairer systems. And I'll give examples for well-being computing and robot-led well-being assessment as well. So I'll mix both. And then I'll look in terms of generation. Also there, the application will be well-being related. And I'll try to conclude with some recommendations. In terms of definition, there are many definitions of bias. So sometimes it gets a bit confusing if you talk to different people from different fields, what they understand of bias is different. The definition I'll be using today is factors that lead to unintended consequences. So this is the working definition I have. And people, again, don't agree on a single definition. It's very prototypical, not agreeing on single definition. So if you write papers on this, you need to say, okay, what is your working definition? So this is ours. And the focus will be types of bias that will adversely impact subgroups of people. So now subgroups of people also refers to these sensitive attributes. So what we mean by sensitive attributes is things like gender, age, ethnicity, even could be things like marital status, things that should not actually have influence on the outcomes, right? If I apply for a job, should be based on my capability, not because I'm, married or not married, or I'm white or not white, right? So this is what we mean by sensitive attributes. And then in terms of types of bias, there are also many different types of bias, but today I'll be looking at 2 of them, so data set and algorithmic bias. And when we say data set bias, there are also multiple data set bias types. So the first one is sampling bias. So this refers to whether my data set is representative of the population in terms of, overall population we are talking about. So if in the world, half are gender-wise, or biological sex-wise, depends how, again, we define this, male and half are female, my data sets should ideally have similar representation. So that's what we mean by sampling. And data management bias, I'll give some examples, but what it means is we need to ensure when we have a data set or we are recording a data set, the way we do pre-processing, the way we do filtering and certain pre-processing steps, it actually does not cause further bias. And you'll see with the examples I give. An algorithmic bias, this is when we train models. So for instance, it has been shown that if you do early stopping in deep learning or quantization, it actually causes bias predictions. So it's good to be aware of this as well. And I'll also talk about this. So let's start with bias in sensing. So I will refer to this guide we published back in 2021, and we call it the Hitchhiker's Guide to Bias and Fairness in Facial Affective Signal Processing. So I'll walk you through this. So usually the fairness or bias analysis can be done at 3 levels. So it could be pre-processing level, in-processing level, and post-processing level. So when we say pre-processing level, what we mean is we have our raw input data, and sort of we look at the original data set before we do any classification. So we see basically, okay, how is the representation? Remember the sampling I mentioned. So how is our sort of sensitive attributes or labels represented in that data set? And then we might need to do certain reprocessing methods on top of the data we have to generate a fairer data set prior to do any training or evaluation, right? So that would ideally give us a fairer data set by the different methods we use. And then in processing would mean actually we are doing this while we are training the classifier. So we have the data sets in terms of training, validation, testing. So it's within the classifier. Again, you'll see some examples. At the moment, it might sound a bit abstract. And the post-processing, we already actually do the detection and prediction. And then we try to modify the algorithm's decision region to achieve fairer prediction. So all of these different steps should give us fairer predictions. That's the idea. Now there are different methods for each of these steps. So for pre-processing, simply the simplest but most expensive solution would be, okay, well, if your data set is biased, just create a new data set from scratch. But of course, this is very expensive, right? Who's going to do this? So then what we can do is we can do data augmentation. It's very well known in computer vision, not necessarily for bias mitigation, but for even just multiplying, getting more samples. So that's data augmentation, helps also with fairness. We can do synthetic data generation. Of course, having now generative AI models, that should also be quite easy. Then we have other methods, which I will give examples. And we can also do sampling down or up or over sampling. And in-processing also has different methodologies. I won't go into detail today. I'll briefly mention and show examples for disentanglement. And as I said, post-processing, again, you could use different things there. Some of the companies have even created black box methods that you could use if you have very large scale data. You could use their post-processing methodologies or APIs for bias mitigation. Okay. So I will first start with a sort of simpler, not yet in the world examples, so to say. So we have this RAFDB data set. It's not ours when I say we. So back in 2019, we started looking at bias in facial expression, facial action unit, and facial affective sort of computing. At the time, there was not much work done in this area. That's why we started with existing data sets. And one of them is RAFDB. So I'll give this as a step-by-step example to walk you through what I mean by all the different definitions I gave you. Then we'll focus on well-being aspects. So this data set has these prototypical labels, emotion labels, surprise, fear, disgust, happy, sad, anger, and
134 IQ. I make less money than friends who barely passed high school. Here's what I finally discovered. Last week, a kid I tutored in high school posted on Facebook.
Then in terms of labels for sensitive attributes, we have gender is male and female. And then for race, we have these different, again, Caucasian, African American, Asian, and age also we have 5 different labels. And the data set looks like this. It's images from the internet. Sometimes people call it in the wild. Some of them are, again, a bit exaggerated, but that's what we are working with. So remember now what we said, first step is to actually look at if there is sampling bias. So assess the subgroup representation. So we look at the representation across these sensitive attributes. And what we see is this data set is biased. So in terms of gender, it's a bit closer, but still there are differences. And in terms of ethnicity, definitely the representation is more geared towards Caucasian population. And in terms of age, it's mainly younger adults, which is very typical. If you gather data sets at the universities, that's what you get. In fact, this population and whoever else is around. So now this is what we have to work with. So what do we need to do? Well, we need to sort of decide, okay, how we're going to evaluate, first of all, if we have this sort of bias and analysis. So accuracy, everybody's familiar with. I'm not going to go through that, but for fairness, it needs to basically, the metric needs to indicate whether a classifier is fair to the sensitive attributes. This is what we want to get. And then there could be different ones, but here we will work with a very simple, it's called equal opportunity. So ideally, the classifier should perform similarly for these demographic groups. So no matter which age, no matter which gender, we should have similar results. That's what we want to say. And therefore, we define it as the minimum, meaning, okay, the dominant group means the ones that are in majority in terms of our sample numbers. So our classifier is as fair as it basically treats the one that is, least represented. That's why we say sort of whatever this minimum number is, that's how our fairness measure will be. Okay, so now step by step. So we can train a baseline model. That's like the first step to see what's going on. And at the time, back in 2019, ResNet 18 was a good choice because it has been used for computer vision tasks. So we basically do expression classification with cross entropy. And then we look at, okay, how are results looking in terms of accuracy, again, broken down by attributes. First of all, what we see is actually accuracy is not that great, considering this is a well-known data set and, they usually achieve much higher results. So it's really important then to remember we can't have a very fair classifier, but that doesn't work. That is like almost close to chance level. Then what are we really doing, So ideally, we have to have this trade-off, an accuracy fairness trade-off. That's what we are trying to figure out. So we can do better than this. Okay, remember I said, okay, we can start with pre-processing strategies. So we could do data augmentation. You could do cropping, rotating, mirroring, histogram equalization. And now if you look at the results, okay, they have improved, right? So this pre-processing method really helps compared to the baseline. Okay, can we do a bit better? Can we improve on model fairness? And there are different definitions. Again, I won't bore you with like exact details of these definitions. If you're interested, you can look at our Hitchhiker's Guide. We explore it there. But based on these definitions, we can also have lots of different fairness metrics, not only the one I showed, the equal opportunity one, but you could have equalized odds, equal accuracy, demographic parity, test fairness, conditional statistical parity, so all of these. And ideally, we should use multiple of these metrics. And for the well-being examples, I'll show you these multiple ones. But now you're just going with a simple example. Okay, so can we improve on model fairness? So one way of doing this would be, now we did pre-processing, right? So we want to now do in-processing mitigation. So one way would be fairness through awareness. What that means is perhaps we can use the labels, the actual sensitive attribute labels as features. So we can actually use them as one hot vector, and we can upsample them and then concatenate them. So again, ResNet 18. So this is one in-processing methodology. Another one is fairness through unawareness. This is also sometimes known as the disentangled approach. So here we have as the primary branch, the expression classification, that stays there. But we also have these parallel branches where we have the confusion and classification. So what happens is here, the confusion part tries to estimate the equal probability for each of the sensitive attributes to make sure that they cannot be predicted from this representation. But at the same time, we also have this classification branch, and that learns to predict each sensitive attribute correctly, so we don't end up in a very sort of trivial mapping solution. And with this, if we now look at the full table, we can really compare. So here, of course, when we say attributes aware and disentangled, it's not just in processing anymore. It means we build on First, we do the pre-processing, so data augmentation, and on top, we build this attribute survey and disentangled. So we are stacking actually the different bias mitigation techniques. And when we do this and you compare all the numbers, of course, you start seeing that actually these two, so having in-processing really helps on top of the pre-processing bias mitigation. Particularly the disentangled approach seems to be performing the best. But what happened to our fairness measure, right? Because these are still accuracy led. And here, what we see is, again, without and with augmentation, if the representation is close to each other. So remember, the gender gap was not as big as the ethnicity or age gap in terms of representation. Therefore, from the baseline to what we can get with disentangled, there's only so much improvement you can make. It still improves, but you see more when it comes to actually more problematic representations where race and age was, if you remember, in terms of the gaps between different groups, there you see more the benefits. And of course, you can also do other, like you can try to group gender and race and various pairings as well. Okay, so we saw that data augmentation is good, but alone is not sufficient. It's quite naive. So if you do in-processing bias mitigation, it actually helps. And here, for the ones we tried, the disentangled approach works really well. So then the question is, okay, what are the different pros and cons for each of these methodologies? Of course, each of them have benefits and disadvantages. So as you saw, pre-processing, the benefit is it's quite easy to do. You don't need to be an expert necessarily, like pure machine learning and designing novel techniques there. So you can easily use it, but of course it's limited in terms of efficacy. And in processing, okay, it requires a bit more knowledge in terms of, how you can actually design your machine learning algorithms to cater for the actual contextual issues. But it's good in terms of performance. Then, of course, it has these other aspects, harder to implement, more time and computation cost, and so on. And post-processing, I haven't shown any examples here. I'll show a bit later. The good thing is, because it's done afterwards, you don't need to retrain your algorithm every time, right? You can just do whatever, and then you can apply post-processing regardless. But because some of those are black box techniques, particularly the ones provided by companies, you don't really see what's really happening there. So they all have their limitations and benefits. So we also did various other works on top of this. I will not have time to go through all of this, but if you're interested, continual learning is an interesting one. So what we did there was we actually treated the sensitive attribute groups as domains, for instance, gender. So male is one domain, female is another domain. And we can learn the facial expressions first for one of the domains, so either female or male. So once we do this learning, ensuring we don't have catastrophic forgetting, we learn for the other domain. So this is an interesting approach because we have this priority of not having catastrophic forgetting. In terms of fairness, actually, it's quite a good solution. So I would just urge you to check this paper if this is something interesting for you. And more recently, just in December last year, we also have this paper at NERBS. So some optimizers are more equal. So here, the exploration is on optimizers and how it impacts group fairness. And here we also explored other data sets like Fairface, MS Coco, CelebA, and so on. Okay, so now I'm going to focus a bit more on the high-stakes scenarios like mental health disorder prediction. So again, when we started looking at this domain, bias in mental health disorder prediction, most of the works only focused on textual-based data. I call them textual because it's like data sets where you have your income information, or for instance, like marital status and so on, but not really behavioral data. And in my group, we focus on behavioral data like audiovisual or multimodal data. So we found data sets that are, what my PhD student calls out of the lab, but like real world data sets, and on different mental health disorder problems like schizophrenia and depression. So we have these three data sets, depression, psychos, and dialogue, and they have different types of data. So two are motor activity, the last one is audiovisual. Again, different samples in terms of sensitive attribute labels. And only the first one is balanced across these sensitive attributes, and the D-log is not balanced. So what we do, what I preached, pre and in and post-processing, so we do all of these different techniques. Now that you know, I don't need to explain too much. So we have data augmentation. In processing, we do loss reweighting. So this penalizes misclassified minority classes at a higher weighted proportion. Then for post-processing, we have the reject option classification. And this one reclassifies the prediction of the minority group in favor of the minority group. So if the predictions fall within certain decision region or threshold, we say, okay, we'll give them in favor of the minority group. Then I will not go through all the data sets because a lot of numbers here, so forget about this one. We'll look at D-log because it's audiovisual behavior and also because it's an interesting and challenging data set. We have the metrics in terms of accuracy F1, but also in terms of fairness, now we have multiple metrics. So what is happening here? So we have male, female, pre-processing, in-processing, post-processing, and you have these numbers. So we see, particularly in terms of fairness metrics, there's not really a conclusive outcome or finding here. And interestingly, here, even though female samples are much higher than male samples, still the classifier seems to be biased. It seems to be biased or biasing towards female. So this is interesting because we assumed, okay, if the majority class in terms of samples is higher, should work better, but that's not the case. So what's going on? So we try to then do these different strategies to sort of resolve this issue. Okay, the pre-processing creates more synthetic female samples. In processing, weight sort of the training algorithm in favor of the females, and post-processing reclassify the female samples in favor of the positive class. So all the things that we sort of mentioned already. But still, we could not improve the results. So what was the potential pitfall? And this is quite typical in research. If you're a PhD student, I would say at this stage, don't give up. This is where the exciting things happen, because usually we just focus on getting high accuracy and then giving up. What we found is the creators of this data set, in fact, did this problematic issue. What was the problem? So the original data set, the whole D-log lengths we see here actually. So females spoke longer. So their videos were much longer than male. But the creators of the data set said, okay, we're going to look at the median or the average, and we're going to truncate and bring them all to a certain length. And if they truncate, what happens? We lose information, right? So we did not have access to the original data set, but we figured out this could be one of the problems. And this is exactly what we mean by data mismanagement bias, because by assuming, having certain assumptions, say, okay, I'm going to make everything more equal, but in fact, you're causing unnoticed bias. So this is something to really bear in mind. Then the other issue is, we looked at the literature, and in terms of depression manifestation, actually, female and male manifest depression in different ways in their behaviors. It's not similar. And if you try to treat it as if it is similar and try to create a generic classifier that will work across both genders, then it might be problematic. So this is another assumption that could be one of the issues. So main key takeaways from here is, actually at that time, the various bias mitigation techniques were inadequate to address this inherent problem, the gap in depression recognition across genders. And then a couple of weeks ago, the World Economic Forum had a panel on women's health. And exactly what we found, they were also preaching there, not necessarily for mental health. What they were saying is, and they had experts, so it was led by Nature editor-in-chief Magdalena Skipper and experts on different areas. So they were talking about different, biological diseases, solutions, interventions in terms of medicine and so on. What they were saying actually is that, if we treat equally, it is problematic because actually there are specific complexities, gender-specific complexities. So Then, actually, we also saw this not only for adults, but for children. So I'm now going to talk a bit about child mental well-being assessment. This is also a project we've been working with the Department of Psychiatry in Cambridge for over 5 years. And the reason is, of course, mental health is not only a problem for adults, but also for youth and for children. And the numbers can vary here. It says 5 in a classroom of 30 are likely to have mental health problem. But of course, depending on the country, on the context, it might slightly vary. But what is important is everybody agrees actually that early detection and treatment is crucial. Because it affects the rest of their lives, right? So if you think of a child 7, 8, 9, 10 years old, if we can do early detection and we can do intervention early on, actually it will impact the rest of their lives. But the problem is their resources are scarce all across the world. I don't know in Finland, but in the UK, US, and so on, it's quite problematic. And schools can be actually a good place to start. But as I highlight here, in the US, only half of US public schools offer mental health assessment. Forget about intervention, just to assess. And what is also happening is actually youth and kids feel there's human bias in the assessment. So they feel like their issues are not correctly understood, or they're stigmatized or discriminated when they reach out for support. So there are multiple layers in terms of problems. Then what we wanted to explore as an alternative solution was, okay, can we use social robotics for child mental well-being assessment? So when we started looking at this, there were not works looking at this aspect. And the reason was because previous works looking at robots and children found that children, particularly if a robot is the size of a child, perceive the robots as peer, not as a toy, and the difference is they perceive parents, teachers, and psychiatrists as authority figures. So they don't disclose their true feelings to them. So we thought, okay, we could perhaps explore social robotics because robots can engage children. You can program them to do different ways of, like even the assessment can be sort of gamified. And then you could put them in schools as well. You could make it more accessible. And also they could ideally help with this initial flagging for assessment. So in the UK, the pipeline for assessment works like this. So we have the childcare space like school, and then the family is contacted by them. If they give consent, then a lay interviewer using prototypical questionnaires, online questionnaires, will ask the child or will walk the child through those questionnaires, will fill those in, and this will be recorded in the system, and then the actual diagnosis will be conducted by the clinician. So what we are proposing when we say let's explore robots is this part. So we say, okay, actually, maybe we could have the robots to do this well-being assessment part, and not only in terms of what the children are saying, not the content of what they're saying, but also their non-verbal behavior. So we can have different activities, look at also their non-verbal behavior, ideally already analyze this and ideally already do initial flagging that will go to the clinicians, and clinicians can still do the final diagnosis. And we started back in 2021 with a small lab-based study with 40 children aged 8 to 11. So we used the Now robot. Here, it's my postdoc. We call it's not a child because for privacy, I can't put children's photos. But before the study, we asked the parents and the children to fill this revised child anxiety and depression scale. It's a very well-known one, advised by our psychiatry colleagues. Then when the parents brought their children to the lab over the weekend, so it was around 30-35 minute session with the robot, then they would do this task with the robot. So they would do memory recall, so share with us a positive memory over the last week or two, negative memory. Then the robot would administer this short mood and feeling questionnaire, and then another one which is called child apperception test, and RCATs as well that they did initially online. So I won't be covering all of this. I'll just give, I didn't check audio, so hopefully it works. Let's see. So this is the picture task.
First picture. do you think is happening with the picture?
Tiger,
Uh-huh.
that's chasing monkey, and they are in a jungle. Maybe the tiger was just angry and she wanted to eat the monkey.
So I'll just repeat in case the Zoom was not picking the audio. So the robot is asking what's in the picture, and the child is saying, I see a tiger and a monkey chasing the monkey in the forest, and maybe the tiger wants to eat the monkey, and so on. So there are different pictures. They come from this child perception test, and it's not necessarily, like it's well known in psychiatry. So we had these 3 pictures, and then the therapist looked at the data based on what the children said and labeled the data in terms of, okay, this child might actually need an assessment. So there might be in the depressed category, this one might not need. So what we did next was we wanted to compare the therapist assessment with visual language model assessment. And of course, being sensitive data, we can't use things like ChatGPT and upload the data on the cloud, but local models, offline models. And the way we did this is first, the VLM prompt consisted of having the CAT procedure information. It's very sort of psychiatric related information. You need to sort of read a bit the guideline. If you don't understand, don't worry. Then we have the child demographic in terms of gender and age. We have the questions and responses. And we also have the specific CAT section and item that's being evaluated. Then in terms of output, we have the multiple choice or item-based evaluation. So for the multiple choice one, the VLM either returned the fitting item or stated no choice possible. And for the item-based one, the VLM output indicated whether the prompt matched the evaluated CAT item or not. So this is probably a little bit of a mystery because if you don't know the CAT might be a bit tricky. But what we see in terms of results when we compare to the therapist assessment is, okay, so for the cases where there is no need for assessment, which means the children have high well-being, the agreement is almost 83 or 82%, meaning actually that's great because we can use VLMs to just filter out the ones that have high well-being. They don't need to end up with possibly with the therapist, right? So this is very good for filtering out, okay, these are high well-being, they don't need further action. But when it comes to the ones that need actually and that probably will get a depression assessment, the agreement level is very low. It's 13%. Then we wanted to explore, okay, what else was happening? So including the children's demographic in the prompt had no effect. And here we see some results. But what we see is VLM incorrectly assesses girls as positive. So there are more false positive assessments for girls. And because including the demographics actually did not have significant differences, we are hypothesizing that this incorrect assessment for girls, again, might have been caused the way they express themselves, not what they say, but how they say things. And remember what I just mentioned about female versus male assessment in adults. So it confirms that not only for adults, already at child level, there are differences. There are differences across genders in terms of behaviors. And therefore, very much in line with what the panel was saying. They were not talking about children, by the way. It was mainly women's health. But I'm sort of linking our research to that. It's more complex than just, saying, okay, let's train a classifier and, it will go do generalize across and it's working well. Actually, there's lots of differences. So there's sex-specific biology. There are genetic aspects. So overall, and this is what this panel was also emphasizing, we need sex disaggregated research and care when it comes to they were talking even about medicine, but here I'm saying for mental health, because this is what our work is showing. So that's probably the biggest takeaway from this part of my talk. Then in the actual paper that we sort of presented back in ISHCA 23 for adult well-being or mental health disorder assessment, we also provided recommendations, depending on the finding recommendations. You can check the paper, it's quite long. I'll just give a few examples. For instance, if algorithmic bias is present despite balancing the samples, you might need to train a separate model for each demographic group. if samples are inadequate. And that's what, we are talking about, is text disaggregated research. If mitigation worsens bias, if it does not address the root cause, then you might need to employ appropriate mitigation strategies to address the root cause of bias. So when I say the root cause, I mean the sort of biological differences, the manifestation in the behaviors are like the root cause. And if gender difference in depression diagnosis is there, we need to work closely with the clinical experts to devise better solutions that address this gender gap. This would be the main sort of recommendations. And once we understood some of these problems, we then proposed more principled approaches. Again, I won't be going through this, but you can check this paper, so fair refuse, referee-guided fusion for multimodal causal fairness in depression detection. So that was in Ishkai 24, following up our previous work. We also have this uncertainty-based multimodal multitask learning for fair depression detection. This was also in Machine Learning for Health conference in 24. Okay, so now I'm going to talk a bit about bias in generation. And remember the figure, so we sort of covered the different, as you see till now, we did not do closed-loop interaction because that was our goal, but when we started exploring, if you start small and then you see, oh, actually there are lots of problems. This is a complex thing. So you need to understand what's going on, try to provide solutions before you sort of put it all together. Because if you put it all together, you don't know if the problem is because of the data set mismanagement, because of your model that you're training, or because of the generator you're using. So it's good to break it down before putting it together again. So I'll be looking at now this generation aspect. And again, the context will be well-being related, this time not assessment, but intervention, and we call it well-being coaching. So, I mean, again, World Health Organization reports mental health conditions are increasing, and then there are lots of problems. So some of the problems are people do not want to actually seek help, or they don't recognize that they have a mental health problem, or they don't acknowledge it. Or they come from socioeconomic backgrounds that, doesn't allow them to actually even explore or consider that they might need help, and they will have the time and facilities to get help. So there are lots of problems. Again, just like assessment, we wanted to explore robotics, this time for intervention. And this was also a fellowship project, Adaptive Robotic Emotional Intelligence for Wellbeing. We just finished last year in April. So for 5 years, we explored different aspects. I'll be just providing like some of the final results, the refined ones. So we created a Vita system. So this was one of the final outputs. And here, the way it works is, we have the user, we're sensing audiovisually, and then we do facial expression, some of the in-house stuff from my lab, but also some of the other APIs. Looking at facial AUs, arousal valence, and the expressions. We also try to see if there is breakdowns in the interaction. This is also sometimes known as interaction rupture in the literature. And then we have the dialogue manager. Depending on what's going on here, the dialogue manager prompts for next action. For this one, we use ChatGPT. And of course, the text is generated and then is sort of played on the robot side. So that's how the system looks. But of course, behind the system, it's not that simple because we wanted to do this just like people do with a therapist or coach, meaning longitudinal, not just one-off, but every week they will come and they will have a session with the robot. And we wanted to focus on positive psychology exercises. And the reason was we were not working with depressed people because actually we first need to see if what we're proposing makes sense even with people who are not, actually in the sensitive group, because people who have already mental health disorder issues, they're in the sensitive group. You can't just test these things on them. It might have other consequences that you might not wish to. So this is what we did. And then the way it works is we actually trained reinforcement learning model. First, offline. So we worked closely with the human well-being coach and therapist. So we had some data to start recording them performing this positive psychology with people. Then we have this online adaptive RL when it comes to the actual study. So the model keeps learning for each person as the time goes. And we have, in terms of observations, we have this, whether there's interaction breakdown or not. We know what was the previous action of the robot. We see the speech duration is important because this is about self-disclosure. So are people disclosing? Are they talking? Or are they silent? So we're looking at these things. And in terms of actions for the robot, this was designed with the therapist, because if apparently we go for therapy, the empathic way of doing, empathizing with the client would be to summarize what they just said as neutral as possible. So this sort of gives them the sense that you hear them and you understood. You can ask follow-up question, or you can change the topic, let's say, and that's what the robot actions are. And reward is spatial valence and speech duration. And the reason is, if the person, for instance, is talking, they're engaged, and they're still sort of positive about it, the robot can actually summarize and for follow-up question, ask another question. But if they're not talking, if they're not disclosing anymore, then the robot might need to change the topic of the conversation. That's how it would work. And we collaborated with Cambridge Consultants. This is a tech company in Cambridge. We collaborated with them for over 2 years. We took our robots to their offices several times for 5-6 weeks over the course of 2 years, and we learned a lot from that. But basically, people were their employees. So we had a room they dedicated to the robots, and they would do these weekly sessions. So I will link this to qualitative evaluation. So looking at bias in generative AI, I will link to qualitative evaluation, and we will look at these different aspects of it, because it relates to very much what AI red teaming is about. I don't know if anyone has heard AI red teaming. Anyone has ideas what it means? No? Okay, that's good. So you can learn today. So AI red teaming, it's like a blue agent, red agent. It comes from these sort of formulations. The red agent is the one that's trying to break in, trying to destroy your system, break your system, find its vulnerabilities, crack the code and break in. So that's what AI red teaming means. So it means systematically actually trying to find faults with the system in different ways, probing from every angle to see if it breaks, how it breaks, so that the developers can fix the issues, right? That's the idea, to make it safer, more robust, and more trustworthy. So actually big companies like OpenAI, they have such teams to sort of try to break and constantly sort of evaluate within their own company. So it links to that, and I'll explain how. So the study was 17 employees from that company with this robot and the system I just introduced. They're doing positive psychology exercises. After 4 weeks, they were interviewed and they were asked about, their experience. So what was their overall impression, how they felt, did they feel understood, listened to by the robot, were there any issues? And then they were brought to a focus group. So this was online. And then here, the idea was finding the issues from the interviews, bringing them to the focus group in an anonymized manner and presenting it as a scenario to discuss. And the scenarios were linked to different ways of HCI. So this might be a bit out of your scope because it's more pure HCI, but it basically links to having different waves. So some are more efficiency focused, and some are more empathy and emotion focused, and some are more social cultural focused. So we'll just look at wave 3, bias and stereotyping. And this is how the whole thing looked like online. But one of the scenarios that came from the interviews is that actually, so one of the employees, when it was interacting with the robot and shared, okay, what are you grateful for this week? And shared that, one of her friends had this great accomplishment and they were sharing this, but the robot, without asking, assumed that the friend is a male. So then this was noticed, and during also the focus group, people commented in different ways that the robotic coach is perpetuating social or societal stereotypes. It should ask more questions rather than assuming the gender, should be trained to use gender neutral pronouns, and so on. And we gathered this, what the robot should and should not do in sort of different categories. So basically, you can use all of these things in a qualitative manner to do this red teaming that I suggested. So there are two aspects to this, right? In the beginning of my talk, I talked about how we can use quantitative measures, quantitative ways of analyzing bias, mitigating bias, and achieving fairness. But until you bring your systems to the interaction, to the closed loop interaction with actual people, you don't really know what their perception will be, how they will feel in the interaction. Because just assuming, okay, your metrics are fine, does not mean their experience will still be the same way you assume it will be. So qualitative aspects are also needed. So this red teaming aspect is also needed. And then you can, of course, act on it and improve your system. That's sort of how it ties in. So I just would like to finish with some reflections. So when we design, implement, and deploy AI systems, we need to ask this question. So are we investigating for whom our trained models work well and why? Do they work for children, for elderly, or is our focus just young adults? Is there any bias? So we need to investigate this and ideally take action. And then, what are we doing to mitigate these issues? So these are the questions we need to ask. You don't need to focus on bias and fairness. You don't need to have a research stream to investigate these questions. If you're building anything that involves humans, it's your responsibility to ask these questions. If you're not asking these questions and you're assuming that your system is fine because it's 85% accuracy, your assumption is wrong. So this is what I would say, based on what I've shown for facial expression, for mental health, for children, and even for qualitative understanding of how people perceive things. And then these are a bit more complicated, of course, but we need to ask also, so if there is these bias fairness issues, does it mean we should never get the AI algorithms out there and really use them, for instance, for societal good, because we are scared now? Well, that's the balance we need to achieve, right? If we constantly actually look at the first two questions that I asked, are we investigating, are we doing something to mitigate, then ideally this should help us to decide, okay, is it fair enough now to make it deemed acceptable to take it out there? Also, we need to ask, is it worth collecting more data to improve the fairness of the algorithms, but at the cost of this individual privacy? I don't have an answer for this question. So this is more reflection. The two of them are for you to reflect as well. If you're working on systems, AI, that is not just in the lab on your computer, but needs to change lives. So these are the 4 questions to consider. And with this, I'll finish my talk. And I would like to acknowledge all the people that contributed specifically to these studies, but also my lab for various aspects of the research throughout the year. Thank you very much.